Hello and welcome to this clip on ligand substitution and precipitation. We'll cover the different types of ligand, how the charge of a ligand affects the overall charge on a complex ion, how we form transition metal hexa-aqua ions in water when a transition metal ion forms coordinate bonds with the water as it dissolves, and the main ligand substitution reactions you need to know for A-level chemistry, including those that involve precipitation. It's assumed already that you have covered some of the basics of transition metal chemistry, including complex formation, what a ligand is, and also coordinate bonding. So this is a hexa-aqua iron 2 ion. We write its formula with square brackets, with the iron and then in brackets H2O and then a 6 after the H2O. We retain the charge in this case because the water ligands are neutral. So the overall charge is dictated by the 2+ that the Fe2+ ion carries. So this takes place, this particular complex will form when iron dissolves in water. The same thing can happen to any other transition metals. They will form a similar type of complex. So cobalt, copper, manganese, for example, they will all do exactly the same thing. So it can be written one of two ways. The second way that shows the water ligands is slightly more informative in that it tells you that there are 6 water ligands coordinately bonded to a central iron ion. But when you see Fe2+ in aqueous solution written the first way, it means exactly the same as FeH2O6 2+ aqueous. So just as a reminder, a ligand is an atom or molecule that has at least one lone pair of electrons that can be donated to a coordinate bond with a central metal ion in a complex. So these are some of the common ligands you'll come across at A-level chemistry. They're not an exhaustive list, but they're the most common ones that they ask you about. You can see that some are charged and some are not. And the colour-coded annotation just shows that the chloride, ammonia, water and cyanide ligands are monodentate, which means they've got one pair of electrons, one lone pair of electrons available for coordinate bonding, and ethane diamine and ethane dioate are both bidentate, meaning they've got 2 lone pairs of electrons available for coordinate bonding. So let's have a closer look at what might happen during ligand substitution. You'll notice that I've drawn the complex that we had on the previous screen again, but this time I've opened up in displayed form one of the water ligands. So now I've added an incoming OH- ion, a hydroxide ion, which I really should have put in the box as a monodentate ligand, so sorry about that, that was my oversight a couple of minutes ago. If we now add dipoles to our water ligand and a curly arrow, you can show a little mechanism by which one of the protons in the water, one of the hydrogen atoms, can actually combine with the OH. And the equation for the reaction is at the bottom of the page. So what I'm going to do now is take the diagram away and redraw it, but this time showing the substituted OH-. So a hydrogen atom from the water combined with the OH- ion that was incoming, leaving a hydroxide ligand behind. Notice that it's now a hydroxide ligand, not a hydroxide ion. A new water molecule is produced in this reaction. So overall, an OH- ligand has substituted for an H2O ligand. And don't forget that there's a change in the charge of the complex ion. It goes from 2+ down to 1+ because of the presence of an OH ligand now, which carries a charge, you can see from the main box on the left. So don't forget to look out for this when you're doing ligand substitution equations. So this could happen again and again. Technically, this new complex could undergo further substitutions till eventually you have a neutral molecule. So let's just summarize quickly what ligand exchange actually is. As the name suggests, it happens when one or more ligands in a complex are replaced by different ligands, as has been demonstrated here. So if you were to substitute another OH- ligand onto the complex we've just made, the 2 negative charges of the two OH minus ligands would balance the 2 plus charge of the iron, and what would happen is you get a precipitate. A precipitation is an insoluble ionic solid formed from the reaction between two solutions containing aqueous ions. You can see that in the third bullet point. What's interesting to look at is the charges on those ions. So once the charges balance between the ligands that are coordinately bonded to the central metal ion and the charge on the central metal ion itself, you'll obviously get a neutral compound, and quite often that will lead to precipitation. You can see that clearly from the photograph underneath where it says FeOH2 solid. So staying with iron ions, in aqueous solution, when they form precipitates from their hexa-aqua ions, the iron ions of different charge form different precipitates with hydroxide ions. So if you look carefully, you can see not just the different colours that you get, but also the number of hydroxide ions that are substituted before a precipitate is formed. So before we look at the precipitation reactions and ligand substitution reactions of copper 2 hexa-aqua ions, just want to draw your attention to the fact that copper 2 plus is a blue colour. And just like the iron hexa-aqua ion, the copper hexa-aqua ion is written in exactly the same way. So although at first glance it looks like a simple displacement, you can also write it as a ligand substitution now we've had a look at this idea. So essentially what we've done is we've cancelled out the spectator ions, which are the sodium plus and the sulfate 2 minus, which we can do in the main balanced equation. So I'm just going to get rid of the diagram of the hexa-aqua copper ion and put in a diagram of what this substituted complex would look like. So when you draw it out, because this particular one is neutral, there's no square brackets, there's no charge. And the positioning of the OH minus ligands can actually lead to stereoisomers forming. So let's have a look at copper hexa-aqua ions reacting with ammonia ligands. As you can see from the diagram in the top right hand corner, we've substituted 4 water ligands for ammonia ligands. This actual process is slightly more complex than it might appear. This actually happens in 2 stages. The first stage is to react ammonia with the blue solution of copper 2 plus ions, as in the top equation. But what happens is the ammonia doesn't quite substitute yet, and there's a specific reason for this. And that's because, as you probably recall from your acids and bases work last year, when ammonia dissolves in water it actually reacts with it to produce NH4 plus and OH minus. And it's the OH minus that does the substituting. So as you can see, there's 2 ammonias, so you get 2 OH minuses when you add ammonia to start with. So the first thing that happens is you get a blue precipitate of copper hydroxide. If you keep adding ammonia, the second reaction happens, and the blue precipitate dissolves and becomes a deep blue solution, because that's when the ligand substitution starts to take place. So in this particular instance, we've got precipitation and ligand substitution happening at the same time. One in the first stage and the other in the second stage. However, you'll be glad to know that these 2 stages, the reactions, don't need to be remembered as such. It's just for information purposes. So you can see that it's a 2-stage process. The next screen takes you through what you actually have to be able to recall. So just to try and simplify a little bit what we talked about, so it doesn't come across as too complex. This is basically what happens. I've put a background writing on paper behind each test tube so you can see what the observation would look like. So to achieve the first reaction, you add ammonia dropwise. And the observations to remember are blue solution becoming a pale blue precipitate on dropwise addition of NH3, finally forming a deep blue solution on continued addition of excess NH3. And what to remember is in the box on the bottom left hand corner of the screen. So far we've looked at octahedral complexes. This is because the relatively small size of water, ammonia and hydroxide ligands enables 6 of them to fit around a central metal ion. So the octahedral shape achieved is due to the smaller size of the ligands, so you can fit more of them around the central metal ion. I've tried to represent this in 3 different ways to help get the idea across. You also get tetrahedral. I'm going to explain to you how come that happens, because that would obviously be bigger ions leading to tetrahedral. But before I do that, I ought to add the charge in on the displayed version I've put in the middle, because that's the correct protocol. Some complexes are tetrahedral, which means you can only fit 4 ligands around the central metal ion. At A-level, chloride ions in particular are a good example, because the radius of a chloride ion far exceeds that of a chlorine atom. This is caused by the presence of an extra electron in a chloride ion, giving rise to additional repulsion between the shells, so they start to move apart from each other. Let me try and explain this for a second. So this diagram is a fairly basic representation of a chlorine atom, including all the shells. If you add an electron, what happens is you get additional repulsion between all the shells. So the ion is obviously quite a lot bigger than the atom that it originally started from. This has consequences for the shape of the complexes that the chloride ions get involved in. So this ends up with a different shape, doesn't it? And it's also interesting to look at the 3- charge in this particular generic example. So assuming that the central metal ion has a positive charge of 1, then that would mean the overall charge is 3-, because you have 4 Cl- against 1 M+. Let's now have a look at a couple of examples of this that come up in the A-level syllabus. So when copper 2+ ions in aqueous solution are treated with concentrated HCl, a ligand substitution reaction occurs, like you can see in the box. There's a few things to notice here. First of all, you have a blue solution becoming a yellow-green solution. Secondly, it's reversible, so if you add water to the yellow-green solution, it'll go back to the blue it started with, but fainter. And also, you can see that there's a change in shape of the 2 complexes. The first complex, CuH2O6 2+, is octahedral because of the smaller water ligands being able to fit 6 around the central metal ion, the central copper 2+. And the second one is tetrahedral because you have larger chloride ions fitting around the central metal copper. So you can see that the charges change as well due to this. We talked about this a couple of seconds ago. So the overall ligand substitution is summarised in the sentence at the bottom of the screen. And just for reference, we can apply this to cobalt, for example, as well, so you can see it's not just copper that undergoes this type of ligand substitution reaction. In cobalt's case, it's a pink solution that you start with, and a blue solution you end up with. It's the same story though, 4 chloride ligands substitute for 6 H2O ligands. So at this point it might be a good idea for me to add a little clarification on the formation of the copper chloride ion, the yellow solution from the previous slide. So if you start with a blue solution of CuH2O6 2+, and you add 4 chloride ions in the form of concentrated HCl. As the reaction proceeds, it turns a greenish hue. This green is due to a mixture of the original blue and some of the new yellow that will be formed at the end. And at the end of the reaction, you'll have a yellow solution. So when I said greenish yellow, what I meant was the sort of tinge that you get. But actually, when the reaction finishes, the solution is a yellow colour. So your CuCl4 2- is a yellow colour. It's important to make that distinction, otherwise it can cause a little bit of confusion between the 2 colours. So I think it's also important to spend a moment having a look at chromium, because that is on our specification. In its purest form, aqueous Cr3+, or to give it its full title, CrH2O6 3+, is purple in colour. But if you substitute one of the water ligands for a sulfate ligand, the colour changes to a dark green. So you can see quite clearly from the photo that it's got a purple hue to it. So let's have a look at some of the reactions that this chromium 3+ ion might undergo. So starting with ammonia being added to CrH2O6 3+, you can see quite quickly that a blue-grey precipitate is formed. However, this precipitate has the formula CuOH3 H2O3. So what's taking place? When ammonia comes into contact with water, it forms the NH4+ ammonium ion and also the OH- ion. It's the OH- ion which is substituting, not ammonia at this particular point. So the overall equation can be written like that. So you can see clearly that 3 H2Os have been removed. So next I'm going to add some more ammonia, but this time to excess. So you may be detecting already a slight purple tinge round about here. I'm going to take another photograph of this when it's been left to sit for about 5 minutes, and we can discuss what we're observing. So now what I'm doing is I'm shaking the solution, and as you can see the precipitate that settled in the bottom has started to redissolve and break up. So the reaction that you can see at the bottom of the screen is the ligand substitution reaction that takes place when you get 6 ammonia ligands replacing 3 hydroxides and 3 waters. And hopefully you can make out a slight purple tinge. That's the compound that's responsible, CrNH3 3+. So, if I add OH- dropwise at first, we rapidly get the formation of the same precipitate we had before, like a greenish, greyish colour. If we continue to add excess OH-, what will happen is that the precipitate will rapidly redissolve to form a darkish green solution of CrOH6 3-. This is obviously another ligand substitution. So 6 OH- have swapped, have substituted for 6 H2Os. So looking at it one more time from the beginning, you start with a purple solution, you end up with a grey-green precipitate. And eventually, on addition of excess OH- in the form of 6 OH- ligands, you get a dark green solution right at the end. So overall what's happened is that ligand substitution has taken place. So now let's have a look at some biological contexts for ligand substitution, such as haemoglobin in the bloodstream. An interesting application of ligand substitution in human biology is haemoglobin. So oxygen, as you can see, can bind loosely to the complex and be carried around the body. It binds directly to the Fe2+. But carbon monoxide can behave as a ligand, carbon monoxide gas. And when we inhale carbon monoxide, it binds more strongly than oxygen to this complex. So this prevents the haemoglobin from carrying oxygen, eventually resulting in death if enough carbon monoxide is actually inhaled. And on another note, the cyanide ligand interferes with the enzymes responsible for catalyzing respiration in a similar way. And these enzymes are also complexes. So the cyanide ligand can form coordinate bonds with central metal ions in the enzymes that catalyze respiration, and in doing so interfere with respiration. But in the case of cyanide, the actual amount required to have a serious effect is much, much, much lower than for carbon monoxide. So cyanide is a much more dangerous poison if it's inhaled, as hydrogen cyanide gas, for example. So for that reason we don't really work with it. We teach you about it when we talk about it in A-level chemistry. We don't work with it in the lab because it's just so dangerous. The risks are far, far too high. So an application of ligand substitution like this might be worth jotting down in your notes and making sure that you're aware of it. It's something they might ask about in exams. So this table shows some of the ligand exchange and precipitation reactions that come up at A-level chemistry. There's quite a lot there, so it might be worth pausing the video clip and doing a summary page of all of these. What I've attempted to do is to use as close to the actual colour as possible to tint the writing, so it gives you an idea of what to say. I've tried to include the formulae for where you have an excess of something that's added. So I've tried really carefully here to make sure it matches the textbook that we're using. In red, I've just reiterated down at the section with NH3 that the initial addition of ammonia just creates hydroxide, because ammonia reacts with water to create hydroxide ions, which then go on to cause a precipitation. On the left-hand side, the reminders of what precipitation and ligand substitution are would apply to any of these, not just the ones that are OH-. That's just the only bit of room I had to put them, but they'd apply to NH3 and Cl- as well. So there's quite a range here, and it's worth spending some time getting them down, and yes, you do have to memorize them, unfortunately. But once you've done a few practice examples, it starts to click, I promise you. But it's well worth doing this, because transition metal questions, long answer style ones where they ask you to explain what's going on and give the observations and equations, they do have quite a high mark allocation, so it's time well invested. Okay, so once you've done that, come back to the video clip and we'll go on and do some exam question examples. So in this question, it says that dilute aqueous copper 2 sulfate contains CuH2O6 2+ ions, just like the ones that we've been looking at. So it says concentrated hydrochloric acid is added drop by drop to a small volume of dilute aqueous copper 2 sulfate. It gives you the equation. We just looked at a couple of screens ago. So they want us to describe the observations that would be made during the addition of the concentrated hydrochloric acid. So the blue solution, which is your CuH2O6 2+, will turn green at first and then yellow-green at the end. And the reason for the gradual colour change is because you start out with a blue complex, but gradually, because it's being added dropwise, the colour change is more gradual. Then it asks us to describe the bonding within the complex. So first what I've done is I've stated how many ligands we've got. I've also stated that they're coordinately bonded, and then I've stated that each ligand, each chloride, donates a lone pair of electrons to the coordinate bond. Let's move the page down a bit. Next one says concentrated aqueous ammonia is added drop by drop to aqueous copper 2 sulfate until present in excess. It says two reactions take place, one after the other, well we've looked at those earlier, to produce the complex ion CuNH34 H2O2 2+. All they want from us is the observations. They're not looking for equations. So the first thing we say is that a pale blue precipitate forms. You don't have to say what the identity of the precipitate is or suggest an equation for it. They just want the observations. And then we say what we would expect to see when further ammonia is added. And as you know, that would mean the precipitate dissolving to form a dark blue solution. So the next question is about the cobalt ion, cobalt 2+. They ask us to say what's meant by the coordination number of a complex ion. So this is best described as the total number of coordinate bonds between a central metal ion and its ligands. And I say it's quite important to emphasize that it's the total number of coordinate bonds, because if you just say the number of coordinate bonds between a central metal ion and its ligands, that could be misconstrued as just saying how many coordinate bonds are there between the central metal ion and each ligand. You want the total number of coordinate bonds in its entirety between a central metal ion and its ligands within that complex. So the next part of the question wants us to draw the shape of each complex ion. So starting with COH2O6 2+, it's no different to any other hexa-aqua ion in that it's octahedral. So you add the ligands, making sure that the bonding is between the central metal ion and the oxygen and water, not the hydrogen. You put it in square brackets, and you put the charge outside the square brackets. And the other one is tetrahedral, as we've looked at during this clip. So let's bring the page down again. Now they want the colour change, and we did mention this in passing, as pink to blue. And it says describe how you would move the position of this equilibrium to the left. So let's look at the equilibrium again. So if we want it to go to the left, looking at the equation up at the top of the screen, we want it to go in that direction. So it would obviously be to add more water. So shall we go on to the next page of questions? So this time it's a multidentate ligand, EDTA4-, and it says complete the electronic configuration of the Ni2+ ion. You might want to go and grab your periodic table for this one. And as the part of it provided takes us to neon, we have to put the remainder in to bring it all the way up to nickel. So let's move the page down a bit more to see the rest of that question. So it gives us the structure of the EDTA4- ion, and it wants us to put a ring around two different types of atom that are capable of forming a data covalent bond with the Ni2+ ion. So both the nitrogen and the oxygen have a lone pair of electrons which can be donated to a coordinate bond. So the next one asks us, stereoisomerism is very common in transition metal complexes, and some have been found to be important in the treatment of cancer. So the obvious one that we need to remember for A-level is cisplatin. And what it does is it interferes with the ability of the DNA in cancer cells to replicate. So let's now have a look at the answers. So bring the page down. We've got blue to yellow green. We mentioned a lone pair in the chloride ion, and we said it was donated through a data covalent bond to the copper ion. or a coordinate bond we said. The light blue precipitate is formed, pale blue we said, and with excess you get a dark blue solution. So it's important to remember that not just going blue is enough, because it's two different shades of blue, isn't it? So you have to be a little bit more specific than just blue to blue, because otherwise it sounds like it's not a change. So we correctly describe the number of coordinate bonds, the total number of coordinate bonds. I would maybe go a bit further here, considering it's a slightly older specification question, this one. So in the new specification, the total number of coordinate bonds that are attached to the central metal ion is what you want. Now, in our drawing, we did do octahedral and tetrahedral, and we used these two. So we got our 2 marks. We said it went from pink to blue. We also said that to drive the equilibrium, the position of equilibrium back towards the reactants, you add water. We went up to 3D8, and we didn't use the shorthand like they've told us not to do there. The O- and the nitrogen had a ring around them, and we had a lone pair of electrons that were available to be donated to a coordinate bond, didn't we? So we put that down as well. We said cisplatin, and it binds to DNA and prevents the cell from replicating. We mentioned the DNA, it interferes with the ability of the DNA to replicate. So that gets us our total. So hopefully this has been a fairly useful introduction to some of the questions you might be asked about transition metals and how ligand substitution and precipitation reactions feed into that. If you've got any queries or questions, do bring them into one of us at college, or maybe have a chat to your teacher, come to a subject extension maybe. But either way, thanks for your time and see you soon.